We're live. Alright, so today we got ourselves here a MacBook Air 11-inch. This one's either going to be a 2013 or a 2014, but it's an 820-3435, and it's not turning on. There's a great deal of corrosion on it. Let's see if we can get this one taken care of in time. So, first thing I noticed was all around here we got a great deal of corrosion, and I'm not well versed in the 11 inches, but I feel like this is going to have to do with our PP3V42 circuit. So let's go ahead and start with our measurements and just see what this is or isn't doing. So let's plug in our DC power supply and see the current draw. And right now we are drawing 0.019. Or 0.020. So this just isn't getting any signal to turn on. Usually when it's that low of a signal, that means that we're going to be missing our SM Sleep S4L line. So let's look at our power rails. Let's pull up our board view software. So this one is at 820-3435. So now we want to look for a page in the schematic called Power Aliases. So we'll just do a neat little search, and until we see a page that looks like it has a lot of lines like this. So here is our power aliases for this board. The first thing we want to look is to check and see, are we getting our PP bus? Is that present? So right now I have the board in this orientation. So right where all of our corrosion's at, we have, it looks like our PP bus is actually going to be close to there. So let's check and see right here on this resistor if we have our voltage for PP bus. So that top one right there is going to be the resistor that has PP bus. PP bus is usually about 8.6 on this model. And our multimeter is saying 0.4 and draining. So PP bus is not present. And I wonder if it could be because of all of this right here. Another thing I noticed too is that our MagSafe is not actually turning on. Just to make sure this isn't an issue with our power supply, let me try resetting the connection. Yeah, so it's still just not charging at all. If I recall correctly, when the customer brought this in, even with our normal charger that's not connected to the power supply, it still wasn't doing anything. So being that we're missing our PP bus, let's see what else could be potentially missing as well. So let's check and see if our PP3V42 G3 hot is present, and that is correct. All the corrosion that I showed you earlier is right where our PP3V42 is located. So let's go back to our microscope here and just check and see, are we getting 3.42 volts? And we're not. We're getting 0.012. So let's check and see if there's a short right there. Got to turn off our power supply so we don't damage anything. And we have a 5 kilo ohm short, or I'm sorry, a 5 kilo ohm resistance, so that is not shorted. So I'd say just because we have so much corrosion here, we should just replace all of this and see what happens. So we're going to need our donor board. And let's see, and the donor board doesn't look that great either. So I have another 11-inch donor board right here, but you can see around the same circuit, I remember this one. This one actually had chocolate milk spilled into it. So, well, the components actually look okay, except for this little thing right here. It's this resistor doesn't look all right, but for the most part, U7090 on our schematic looks okay. Let's check and see what U7090 is. U7090 is our 3.42 generator, and we're not going to get our PP3V42 if our PP bus is present. So let's check and see what actually controls what creates our PP bus. So I'm just going to copy the PP bus information and kind of go further up the line until we see what creates it. All right, PP bus is going to be created by our ISL right here. It's a U7100. U7100 is located right here on the back of the computer. Alright, so here's our ISL. And for visual inspection, all of that looks okay. Our SMC looks like it's got some junk right there as well. Alright, we're back. I had to step away for a second. Just out of curiosity, I'm going to see what this component is. Okay, that's going to be a resistor that connects our PP342, which is not present to our CPU thermal trip, so that actually has nothing to do with it. So before I get too off track, we could do a couple things. We could check to see if our ISL is even turning on. But being that we have so much corrosion, let's just go ahead and replace all these parts. Okay. So what's the name of this component? I think it was U7010. U7090. Alright, so next to U7090 in this giant capacitor, there once existed a resistor. That resistor is completely gone. Let's check and see what our donor board looks like. Those parts are there. So we're just going to take off these components and replace them entirely. So there used to exist a resistor right here, and now it's just marinated, it's charred. I may have put the wrong size tip on here. I was doing some iPhone repair earlier, so this might not come off as easy. Yeah, it looks like that's exactly what happened here, is I just didn't put the right nozzle on. So we can do a little bit of cheating. Add some more flux. And we're going to take our tweezers and heat up the pads while we're also heating it up with the rework station. Alright, so I'm just going to set that aside. And all that came off pretty easy. Now before we do anything else, we have a lot of gunk here that needs to be cleaned off. Yeah, it looks like our issue's probably going to be around with this generator chip. And we have some ugly looking pads, so let's just tin that up. Much better. Have a little bit too much solder on that ground pad there, but we'll be able to take care of that here in a moment. So now let's switch over to our donor board, and we're just going to borrow these parts. By borrow, I mean transfer. Okay, we got everything prepped, so let's go ahead and start removing. Come on, little regulator. You need to say goodbye to your home. I really just need to change it out to my larger nozzle. Just the thing with the Quick is when you use it, it heats up, so it expands the metal onto the airflow gun itself. So it's harder to remove the chip once you've put it on. Or I'm sorry, it's harder to remove the nozzle once you have it on, because you gotta wait for it to cool down. Okay, let's grab these capacitors. Just bring them on over. And we have one little resistor left. Yeah, I just loosely put all those components there because we're going to be able to lay them in a lot better once I heat up this area anyways with our rework station. You good up there? Alright, so we got some giant balls sticking out of the generator right here, and we're going to touch that up with our tweezers. I want to make sure every leg is touching. Yeah, that looks good on the right side. Let's do the left side. Left side looks like it could be touched up a little more. Okay. That's smart. If a hard drive is really bad, it'll actually prevent you from booting into another operating system. Is it a 15-inch? 13? Okay. If the fans are on high speed, then that means that there's a thermal sensor issue. So the next step is going to be to open it up, just to make sure there's no signs of liquid damage. It's going to make the CPU load slower because it's throttling itself. So it will make it just naturally run slower, but were the fans running at high to begin with? Okay. Okay, and I just realized this diode over here, it's hard to see in this camera, but it doesn't look the best. Yeah, there's some gunk here that's connecting these two legs together. Just cleaning it up. Let's see if that did anything. So what we did was we just cleaned up our PP3V42 power generator, and we switched it out with one from a donor board. So let's see, did we get a light now? We still get, oh, we're getting actually some pulsing now, but it's very low. We're getting 0.006, 0.010. So we've done something, but we haven't fixed the issue yet. Now I'm curious to see if we even have our 3V42, if that's present. We're getting 1.6. It's still low, but it's a lot higher than it was before. And we have a great deal of corrosion right here as well. So now let's check and see if PP bus is present. We got a little fuse. This is normally PP bus. PP bus is still 0.4 and draining. So now my question is PP bus turning on, but then it's turning itself off? All right, we went to 0.6. And now it's slowly going down. All right, so it's like PP bus is trying to turn on, but it's not actually turning up all the way. So that wasn't our issue. So we're not going to get our PP3V42 if our PP bus is missing. So let's see what we can do to get PP bus working again.
Let me go ask about that real quick.
Oh. Alright, now let's check and see what's going on. That's gonna be, it's a piece of plastic. I'm not sure where that comes from. Metal?
Yeah, like it's metal. It might just be something random that just got jammed in there.
Yeah, that doesn't look like that goes in a Mac.
Okay, cool. So yeah, whatever this little metal piece is, it looks like it may have.
Alright, so right here is going to be our PP bus fuse. No, this isn't a. Yes, PP bus fuse right here.
Okay, no problem.
Well, let's check and see if there's anything that's pulling it
No,
down.
we do not.
So we'll just put this into our ohms mode.
No problem.
And nope, looks like it's perfectly fine. Alright. Okay, sorry, phone calls started blowing up. So now let's kind of inspect to see if there's anything else that could potentially be pulling down our PP bus. So I'm just looking around on the logic board here.
Let me go ask real quick.
I'll be right back. Okay, so now let's check and see if any of this corrosion here could be one of the reasons.
Have that name in the system.
So this MOSFET here is Q7006. Does this have anything to do with PP bus? This is going to be part of PP bus, actually. So it's possible that our PP bus is fine, but once it hits this MOSFET to go to the backlight, maybe that's pulling down PP bus and preventing it from turning on. So let's check and see if any of these components have any obvious signs of shorting. So
No problem.
that doesn't look healthy. Yeah. And we have a little test pad right here. Hopefully that's just a test pad and nothing else. But that test pad looks like it's gone. This is a fuse for the LCD backlight that looks like it's gone. Just to test it out, let's put our multimeter in continuity mode. Yeah, so it's not beeping, so our backlight's gone on this one. This doesn't look healthy, but it says that it's fine. And then all this looks really bad. So I'm going to clean up this area and just kind of touch up that MOSFET. Theoretically, we can remove the MOSFET and the computer should still boot up without it. Because that MOSFET, its sole purpose is controlling our, is going to go and turn on our backlight. So I can actually just clean up the area and remove the MOSFET and see if PP bus exists. Well, actually, now that I'm looking here on the schematic, the MOSFET doesn't have anything that goes to ground immediately. We do have other MOSFETs, so like Q7707 right next to it. That could go to ground. So I guess if this is damaged, that could technically ground out all that. No. Just kind of thinking out loud as I work here. So I don't think that's the issue, but that test point definitely looks a little suspicious.
Okay, so after disconnecting the SATA cable from the hard drive, the fan's definitely quieter,
Mm-hmm.
and it booted into our operating system.
So definitely a bad hard drive.
Okay.
So now what you'll need to do is we'll need to pull the hard drive out, put it into a SATA wire, and see if we can detect it on one of our computers to see if his data is fine.
Okay. So yeah, it's definitely a bad hard drive. I disconnected your hard drive from the computer.
Alright, so I'm just kind of cleaning up right here, because we have these test points that are just destroyed.
And it booted in. So it's definitely a bad hard drive. If you have another device, I'm gonna pop this out and see if I can see it being detected on our other computers, and then that will definitely let us know. That way we can
Yeah, because the only thing that could really go to ground here is going to be this MOSFET, so that theoretically could be bad. You know, that corrosion there definitely doesn't really help out. Still not getting any charge here. Okay. For the sake of science, let's check and see, now that our computer's on, if PP bus is shorted. Nope. So why is it that PP bus has 0.6 volts? What is pulling down our PP bus?
Can I just use the wavelength instead?
Mm-hmm.
Okay. I'll just use that instead. That one's more reliable, I feel.
Aha. So all this around here looks like this could be bad. So this is going to be our backlight chip. This is the driver that's actually responsible for backlight. This could be one of the reasons why, if PP bus is somehow being pulled down by this. Oh yeah, that looks like junk. Let's see, does PP bus go over here? Doesn't look like PP bus is directly connected to it. But it doesn't look good. It needs to come off anyways. The computer will still boot up without it. We just won't have backlight automatically. So we are technically missing a PM Sleep S4 line, but that's normal because we don't have all of our other lines. So if we're missing all of our main lines, like our 5 volt line or 3 volt line, then we're going to be missing our all-sys power good signal. I just realized you can't see what I'm working on. I need to have some sort of button to help me switch back and forth between cameras, but so we're missing our all-sys power good signal, so we're automatically going to be missing our PM Sleep S4L because our PP bus is not present. So we have to fix PP bus before we can get anything else working. And just because this is heavily corroded, I'm removing this. We don't need this anyways. Oh, we don't need this for troubleshooting. We'll need it for having backlight to work, but we need the computer to turn on first before we even start worrying about backlight, and I'm not going to leave that chip on there anyways. We have replacement chips. Now, this I think is going to be our 3.3 regulator, the chip underneath it. Let's check and see. U3210 is, yes, our 3.3 HV power mux. If I remember correctly, yes, this is what connects or creates 3.3 volts into Thunderbolt. And it's got a lot of gunk on it too. So this could potentially be bad first. Or bad as well. Let's check and see if there's any other obvious signs. Well, I don't like that component anyways. Oh, once again, you can't really see what I'm saying. I'm so bad at this right now. So that component we said is a resistor. It's our PP3V42 that goes directly to our CPU thermal trip. Let's check and see what the resistance of it is. So this is going to have a 100 kilo ohm resistor. So if we were to measure this in our resistance mode, what are we going to have? We're getting 99. So despite that component looking bad, it's actually working. So that's fine. So we need to go back to thinking. Something is pulling down our PV bus here, preventing the entire computer from turning on. So I guess what we should also check before PP bus is going to be, we need to check that ISL again. And I think I kind of glanced over on that part. So let's take a refresher. I'm sorry, I got a little confused. We had a couple of customers call and people come in, so it's kind of thrown off my mental thinking here. And I got a big cowlick right here, it looks like, from sleeping. So let's start from the beginning. Let's check our power rails. So just like what we did before, let's check and see if our power rails are present. So we want to check our power aliases. Power aliases. So let's check and see our PP bus. PP bus is, we know it's not present, but let's just go ahead and pretend like we're starting this from the very beginning again. So our PP bus, just to make things quick, I'm not going to switch the camera over real fast. So our PP bus is 0.6. Okay. Let's check now to see our PPDC G3 ISOL. This is going to be, or right underneath the PPDC G3 hot, this is going to be the power that goes from our charge port directly to the rest of the machine. So that comes from our charger, and it's going to be right next to where all of our corrosion was. So let's take a look underneath the microscope for this. And there is some corrosion there, but there is underfill or overfill. And software is a little hard to interpret, but so we are getting 18.5. So we are getting power from our MagSafe going to the rest of the machine. So it's not an issue with the MagSafe board. Let's check and see if we know our PP3V42 G3 hot is missing, and it's actually this coil that's directly next to the things we worked on. We're getting 1.6. So it's like it's trying to get power, but it's not actually powering up. Let's check our PPV RTC. This is going to be our clock generator. Okay, so our clock is right here in the middle of the board. Okay, so here's our clock, and we need to be getting about 3.3 volts. And we're getting 1.6 when we should be getting 3. So this is low as well. Okay, we got to keep that as a mental note. So now let's go to our PP5VS5. Maybe our ISL is messed up, which is not powering our PP3V 5VS5 3V, our PP5VS5 PP3V 3S5 generator is not working, which is probably not triggering the ISL. I can't tell.
Oh, I just thought you could by the
Yeah, it's a 10S Max.
Okay.
Yes.
So yeah, you have the XS Max.
Okay. Okay, so now let's check and see if we have our PP5VS5.
Like as soon as you open it, this will.
Oh,
How you hanging in over there, Jerry?
and
Do you have some questions?
a little bit
Okay.
like a mid average
Interesting. So we're getting a negative voltage. So we're getting 0.003. We'll turn off the power supply just to see if it's something about the same. Yeah, it's so we're not getting PP3 VS3 at PP 5 VS5 at all. That's completely missing. So now let's check and see if there's a short. There is no short. Ooh, whatever this is. That looks a little burnt up. Okay, so we know that our PP3V3 is actually pulling down to about 1.6, and our PP5VS5 is not present at all. So now we're going to have to check our generator, the U7501, according to the schematic here, and check and see why it is that we're missing. I got to be right back, though, just to help out some customers. Okay, we're back. Just had to take a quick intermission to help out with some customers. So where we last left off was we know that we were going back down our power rails just to see what was missing, and our PP bus is pulling 0.6 volts. So something's pulling it down, or it's just not getting enough power to boost to turn on. So our PP bus is going to be created by our ISL, and the ISL looks like that is powered by our 5-volt rail. Well, we're missing our 5-volt line, which is generated from U7501, and our 3-volt rail is only generating 1.5 volts instead of 3.3 volts. So now we need to find out if U7501 is even being told to turn on. So let's check out the information on the schematics here. So U7501 is our I can't speak. 5V, S4, S3, 3.3, S5 power supply. So, interesting. This doesn't generate our 5-volt S5. This is going to create basically our hibernation and our sleep mode for 5-volt, but it does create our 3.3 always present power line. Well, not always present, but our S5, which means off. Our always present is going to be G3 hot. So, let's check right here at the very top. Pin 23 is voltage in. And voltage in is going to be generated from PP bus S5 high side ints. So if we're not getting our PP bus, then this isn't going to turn on this chip. But we're also getting a very low, like 1.3, 1.5 on our 3v3. And we can see right here, here's our PP3v3S5 is going to be coming out of all this. So something's still pulling down our PP bus. Okay, so maybe U7501 comes on after our ISL. So we need to check out our ISL, which is U7101. Or I'm sorry, U7100. Okay. So U7100, ISL 6259. We do have those in stock, but we can see this is going to be our PP bus supply and battery charger. And we can also see right here at the very end, PP bus G3 hot to system. And we're only getting about 0.6. So something is either not being fully created or something's pulling down our PP bus. I didn't see a short earlier whenever we were measuring in resistance mode right here on this fuse. F7140 in this specific board. So let's see what's going on here. First, let's check and see if we're receiving power. So VDD and VDDP, it's going to turn on from PP5V1 charger VDD. Let's check and see what power we get. This says this should be about a 5-volt line. So right next to our ISL, we have this giant capacitor. We're going to measure that. There is said capacitor. And we are getting 5 volts. So we are getting our VDD. Now are we getting our VDDP, which is on, it looks like the other side of this resistor. Yes, so right here. Yep, so VDDP is present. So this chip, the ISL, which generates our PP bus, is getting power. So now we need to find out, is there anything else that is just not turning on this chip? So I always like to look around the current sensing around these because they're very, very sensitive. So we have right here our charger CSI. This is going to be our current sensing. We have our positive and our negative. So between pin 28 and 27, we're going to have a measurement of about 22. So we can see from pin 28, it comes up, goes up this rail, and goes to R7121, which is a 10 ohm resistor. It then goes over here to this shunt resistor, which is our R7120. This is going to measure just a tiny, tiny little drop between, what is actually, I think our inrush, and then whatever the difference is in resistance between this resistor is going to determine how much the computer is actually consuming power-wise. But that's a 0.02 resistor, and it comes back here through our charger CSI RN, which is also another 10. So 10 plus 0.2 is going to be 20.02. So we're just going to measure the difference between these two pins right here. So if we look, that was pin 27 and 28, which are right here on this capacitor. So we want to make sure we turn off our power supply so we don't short anything out. Put our multimeter into resistance, and let's see what we have. We have exactly 20.2, so that looks to be perfectly fine. Now there is another part of the current sensing resistor. So we can see right here, we can see CSOP, CSON. So this is CSIP, CSIN. So this is probably going to be I and O, which is, actually I'm not even going to get technical. I'm not sure, but I just know IO typically is input output. We want to make sure that, so this is going to be our input, then this will be our output current sensing, if I had to interpret that. So let's check and see. So our CSOP goes to a 2.2 resistor, goes to a 0.01 shunt resistor, and then goes back to our 0 resistor. It's almost like a fuse. So we should have a resistance of 2.21 or 3, anywhere between there. So let's check that, and that was between 17 and 18, I believe, is what it said. Let me double check that. Yep, 17 and 18. .6. So it doesn't look like it's anything to do with our current sensing. Well, let's find out if it's actually putting out any voltage. Let's see, what else would need to be present? SM bus, SMC 5G3. Let's see, charger reset L. Oh yeah, I guess we would need to be receiving a signal from our SMC reset L. So let's check and see if that is present. Actually, hold on. Before I get too caught up, let's check and see what the output is. So we have our charger phase, charger boot, and then we have all these different gates. Let's see if SMC BCAC OK is being generated. This is going to be a signal that turns on once ISL is working and talks back and forth between the SMC, the system management controller, which will then generate, or which will then make its way to the charger to turn on a green light. So that is 14. Let's see if that is present. .6. I don't know if that's normal, but we are getting some sort of signal. So the only way to really confirm is if we had a donor board, but I want to say that that's okay. So it looks like the ISL is turning on. So now we're going to have, this is always the part of the ISL that confuses me, but we're going to have a MOSFET right here, and if I remember correctly, this is like a boost. Looking around, I've always had a hard time understanding this part. Okay, so we got, just to make sure, we have our PPDC in G3 hot from adapter, which goes into this inrush limiter. Yes. And then the PPDC in G3 inrush is then going to come down here, which will then go to this MOSFET, Q7130. So let's look for Q7130 and check pin 2 to make sure that we have some voltage coming from our inrush. Q7130, which is this giant MOSFET right here on the other side of the board. Okay, so Q7130 looks like something spewed out of the bottom of it, so it might be bad. And what we want to do is check our pin 2 to see what is going on. Okay. Pin 2. Okay, so right here, let's check and see. We're getting 18 volts. So our inrush limiter is working fine because we are getting the proper voltage out. Now let's check and see if what our pin 1
Mm-hmm. On a 6S, it was liquid damage a week ago. He took it to a couple other places. They dried it out and they said it's just dead.
Mm-hmm.
So, data recovery.
For data recovery on a 6S, we would do it for a flat rate of 300.
Okay. We do that for 300 on that.
Okay, so what I was checking earlier was we want to check right here pin 1, and pin 1 is pulling out, it had some voltage for a second. It's at 0.5 and going down. So it's half a volt and dropping.
Oh, like in a lake? Oh, okay.
Yeah.
That's definitely been the story lately. So you're not
Half a volt and dropping. Okay. And I think a second ago, it actually went all the way down to 0 volts and then tried to turn itself back on. So yeah, it's at 0.4. So what would cause that to happen? If we look here at our schematic, just so I can understand that a little bit more. So that's going to be our charger U gate. And then we have a charger L gate. Okay.
Would we be able to do like a whole backup type thing to where if he wanted to put it on a new phone, he could, and it would just text messages and everything?
Yeah. Yeah, we do that with the data recovery.
Okay, so we do both options.
Mhm.
Where one is in PDF form and one is in actual.
Yeah, we'll make an iTunes backup, and then we'll also extract the raw content, so there's 2 copies.
But regardless, you'll have another option that has and then all the
So that would include all like the data that goes inside the adapter on that.
I don't think so. That wouldn't include any app data, would it? Because that would be the apps themselves, right?
Whenever we do an iTunes backup, it will get pretty much the raw data. It'll get some app data, but not all of it, because some app data is actually stored on the app, like on the app server side. So like Facebook, for instance, it's not stored on the phone, it's stored on Facebook. Yeah. Okay. Sorry about that.
Apps I have on there, I'm a digital artist, and it stores all the artwork that I have locally on the phone itself.
Okay.
It doesn't have any cloud storage that it goes to or anything.
Okay. So okay, sorry about that. So one thing that I was noticing here was that we were getting, let's see, so on this ISL 6259, we were getting a 0 on our charger L gate, and I don't think that's right. um, so what I would say here is, let's see, yeah. So this is starting to look a little suspicious here. But at the same time, ISO could be turning on and then turning off. So let's try just replacing our Q7130 and see what happens. Conveniently, we have a perfectly intact Q7130 off of our donor board. So let's go ahead and pull it off. No. Actually, before I forget, let me go ahead and change out my the tip of my quick. I'm gonna want something a little bit bigger. Now that either I'm doing something wrong or this is just really, really on. There it goes. Yes.
He's gonna think about it just for a little bit.
Okay.
Now, if he waits a couple weeks or whatever, that's not gonna be detrimental. Wherever he took it to already dried it out and cleaned it out. It looks
Mm-hmm.
decently clean inside. But that doesn't say anything underneath the board and everything.
Yeah.
So,
If it's already been dried out, then
shouldn't grow any more fungus.
exactly, yeah. Because we'll have to do a board repair anyways to get it working to extract the data. All right. So now we got our new tip on. Oh, so this is going to be our donor for our Q7130. And to kind of help heat it up, these pins right here are all one pin. So I'm just heating up the area. Alright, so this one always takes a little bit longer because we have a ground, and it's a large ground too. So I'm going to heat it up with my soldering iron. I'm just touching one of the ground pins, just enough to make this weak, or malleable. Yeah, it's a good thing I switched to a larger tip because I have more surface area to cover. Yes. Alright, so now we have our donor removed. Let's work on our patient board. Make sure we keep the same orientation. So it's going to come out with the pin 1 in the top left. And then just to help speed up the process, like I did earlier, I'm going to touch the ground pads, as well as this pin up here. I'm just lightly applying a little bit of heat to that part of the ground. I don't want to force it. So we can see that the whole chip has moved. And we're still kind of heating up the general area because we're still soldered onto the ground plate. Okay, and then just to make sure that this melts a lot easier, we're going to add some of our solder, our leaded solder. Oh. Add some of our leaded solder here. It melts at a lower temperature. And that capacitor down there at the bottom, we're going to fix that when we heat up this replacement MOSFET. Yes. I almost put the wrong one back on. So while the board is still hot, let's apply some flux and get the replacement MOSFET on. And go around in a circle to heat up all parts of the pads. Almost there, so it's starting to wiggle into place. Up in the top right, just need to melt a little more. Beautiful. And we're going to fix those solder balls in just a second. Let me fix this capacitor down here. Like nothing ever happened. Let's get our tweezers and just kind of touch up these solder balls. And of course, what I should have done is, since we had 0 on the other side, let's make sure there's nothing shorted over here. Ooh, okay, that's ground, so that's normal. Okay. That looks all okay for the most part, so let's let our board cool off before we do anything else to it. I'll be right back. So now it's been some time for this to cool down. Let's see if replacing that MOSFET that generates our PP bus at the end of ISL, if that is present. And looks like that didn't change anything. We're still getting 0.06, so that was a a mis-soldering repair, which means this MOSFET's perfectly fine. Okay, let's look back here. We might have an ISL issue then at this point. Okay, so if we look back at the MOSFET, let's check and see. Okay, so according to our schematics, we have on pin 1, let's see, of our U gate, this is going to go to Q7130, which should put out about 8.6 volts. And then our charger L gate. So let's check and see on pin 1 and pin 6 if there's any change in what we did. Alright, so pin 1's all the way up here. Still getting 0.4. And then it turned off. So we went to 0.4, 0.3. So it's like it's getting power, but then it's going all the way down until it turns off. Okay, and then let's look at pin 6, which is going to be, looks like all the way over here. Nothing. So now, being that the MOSFET doesn't look like we can blame him, sorry about that, it's possible that either ISL is bad or we're still missing a couple of things that are to turn on the MOSFET, like our SM bus, SMC, 5G, 3 SCL, our clock, and our data line. I think I asked this before, but I don't know if we checked our charger reset L. Because this should be high, and if it's low, then it's going to be preventing this from actually sending power out on pin 13. I could always go for a burrito. Chicken. Pollo asado. Grilled chicken. Okay, so let's take a look back at our U7100 here. Yes, please. You can use the tip money too. We still have tip money up front. Alright, so let's check this component right here to see if it has any voltage. And it doesn't. 0.1. 0.0.1, actually. Okay, well, let's make sure that there's no short. There is no short. Okay, let's see while it's on if something is triggering it to short. It's low, for sure. So something is pulling it down. Interesting. So what I've discovered here is that our charger reset L is not present. So kind of like what the name entails, when our charger reset, it's acting as if the computer, I guess, just did a SMC reset, which is then going to shut off the power to our ISL to prevent PP bus. So if charger reset L, if it's in the low state, then it's going to think that the charger is being reset. So let's check and see if we're even getting power between our 7100. Right here. Really, I could just check and see if we have any resistance. Or no resistance, really. It should be a 0 ohms. It's exactly what we have. So we are missing our SMC reset L. So if this is missing, then it's not going to send a signal to turn on our ISL. So I should have checked that as well before I replaced our MOSFET like a dingus. So now let's check and see what creates our SMC reset L. So if we look here on our board view, that's going to come, it looks like it connects to U5110 and the SMC itself and that JTAG connector. So it looks like it's going to be generated from U5110. U5110 should be our SMC reset switch. Yes, it is. Okay, so this is not turning on. If this is not going to turn on, the rest of the machine is not going to turn on. Why won't you turn on? And here's where we go into a rabbit hole. Damn it. Okay, so U5110 is not present because PP3V42 G3 hot is not present. We know that that's not present. So it's not going to... I'm so confused. Okay. We know our PP3V42 is not present. We know that for a fact. Let's go back and let's look at our PP3V42. And that is going to be the U7090 we replaced earlier. All right, so U7090, voltage in comes from VN G3 hot, PP3V342 G3 hot, which then is going to come from our PP bus G3 hot R, or if we had our battery connected, wait, no. Hold up. So we have our PP bus. And then PP bus G3 hot R. Battery connection. If our battery is present, then this specific line will be present. So what this diode does right here is it has two different inputs to power on our P3V42. So this top line right here, BAT, this is going to be our battery line versus our PP18 5V DCIN ISOLR. This is going to be a direct line from our charger. So our charger should then still, regardless of PP bus, we should still get our 3.42. Oh my god, I am so sorry. Okay, so PP bus 18 V5, this is going to be our 18.5 volt rail coming from our MagSafe. Needs to go through this diode, which we saw earlier looked like crap, which then is going to turn on our PP3V42. So first thing we need to find out is PP3V42 even being told to turn on? So let's revisit our board. God, this is horrible. You work on these all the time, but then you forget about them. Okay, so here's going to be our U7090. Okay, so U7090 is this component that we replaced earlier. So first thing we need to find out is, are we even getting power on our pin? It looks like pin 6 is our voltage in, which is going to be that capacitor directly to the left that we replaced earlier. So let's put this into voltage and check and see what we get. Power supply turned on, 2.7. Now, that's not enough power for this to actually turn on. So our PP3V42 is not turning on, or it's being pulled down. So one or two things is wrong. Either that diode right here is not sending power, or this is still bad. I still replaced this with the wrong one, and it's pulling down our line. So we should be getting about 18.5 volts to turn on our PP bus. So let's revisit, if we look here on our schematic, our D70, our D7005, or D7005. Okay, so pin 2 is the bottom. This is the part that's going to be generated from our battery. Let's check on the other side of the diode to see if we're even getting 18 volts. So this resistor right here, which is a 10 ohm resistor, let's probe here and see what we get. We're still getting 2.9. All right. 2.9 is not 18 volts. So if that's not being present, and let's make sure that there's not a partial short. No, we have 1 megohms. Okay, so back here onto our schematics. On this resistor, we were getting about 2. In fact, I actually didn't even check the other side of the resistor. Let's do that real quick. Okay. All right, so what I've just discovered is we are getting 18 volts on the left side, or pin 1 of R7005. We're going to have a 10 ohm resistance, very nominal, between one side of the resistor and the other. But on this side, we're only getting 2. So we're either going to be getting something that's pulling down, like a bad U7090, or this is this is not working. This is bad. Let's check and see what the resistance is then. So we'll put our multimeter into resistance. Remember, this should be 10. And our multimeter says 6 kiloohms. That's not 10. Ah! I replaced unnecessary parts. Oh my god. Okay. Let's get our tweezers, and we're just going to we're going to pull that part off. Actually, before I do that, let me look at my donor board and see what the resistance is. 10. Yeah, we have a bad resistor. This entire time was a bad resistor. Okay. Why? Why you troll me? Just go. I'm tired of looking at you. I think this stream is over an hour long. Okay. That's gone. Get out of my life. Let's get our donor resistor. I'm sorry for blaming you earlier, MOSFET. Sorry for blaming you, ISL. You weren't even being told to turn on. I'm sorry for blaming your PP3V42. You weren't even getting enough power to turn on. Okay, and of course that looks bad, so we're gonna fix that real fast. Okay. Welcome back. Okay, now make sure we're still getting 10 ohms. We're getting 10 ohms now. Is this also bad? 5. According to schematic, it's 4.7. That's close enough. All right. Are you working? Please turn on. Let's see. Green lights. And we're getting 0.7 amps in a fan spin. It's turned off. Turn on. Should turn off one more time. And turn on. Beautiful. All right. That is a successfully working logic board, almost. Now, if you recall earlier, we also had a lot of damage around our backlights. We had a blown fuse, our backlight driver looked like crap, so we need to repair that too before we call this fully successful. Oh my god. So we can see right here, that is disgusting. So fuse is blown, that MOSFET might be bad, that capacitor surprisingly was okay, LVDS connection looks all right, but we definitely have a bad driver. So let's just go ahead and replace that real quick. So that driver particular, I know we have it in stock, but I can never remember the name of it. So let's pull up that specific IC. According to the schematic here, what is the name of this chip? This chip is a LP8550. Here it is. Okay, so let's check the orientation. It looks like pin 1 is going to be down here on the far bottom left in the way that I have it set up. In fact, it looks like we might have some damaged traces after this too. I don't know if you can see that, but this right here, this looks like it's just dirty. Huh. It looks almost severed, but it's still there. Never mind. That's fine. Okay, so let's grab one of our LP8550s. These we got in bulk from Mouser, but if they're sold out, because this is a very common chip, you can always reach out to store.rossmann group and get them directly there. So remember, pin 1 is going to be the bottom left, so we're going to have to put that dot in that orientation. I'm going to turn down my air output just so that we don't blow the chip away. Now I'm going to heat it up from a distance and wait for it to dance into place. I should have just started out with the power rails to begin with. What I started doing was just looking at the corrosion. That PP342 generator, or the U7090, was probably perfectly fine. It just wasn't getting enough power to even turn on. And that MOSFET was perfectly fine. So I'm just waiting for the chip to kind of dance into place. So again, I'm using a very low output of air. Forgot what the technical term is. It's like CFC or CFM. Alright, looks like the bottom right is dancing. Top left hasn't moved just yet. Okay, it's starting to move. Almost there. Okay, let me heat it up with a little bit more airflow now. In fact, this whole area looks bad. Let's just heat up this whole area. Okay. That chip is good. I'm still very concerned about that test point. Nope, actually, as I dig deeper, it is severed, so that needs to be repaired too. So to repair it, we're going to have to run a wire. To run a wire, we're going to have to carve into the trace. This resistor, in my opinion, looks like trash. Goodbye, resistor. You called the guy with the iMac? Sweet. Can you get the other iMac that's on the floor back there and just start removing the screen? That one, we need to diagnose why the LCD is not turning on. So now that we've carved a hole into our trace, let's add some solder. Beautiful. Okay, so we got a giant blob on there. We'll be able to fix that, but now we need to get a resistor from our donor board. Hands are very shaky today. I need to eat. It's because of the orientation I have this at. I sprained my wrist, and so it's still a little hard to solder. Okay, so we got our trace on there.
I get the same dude that messages Eric Jones on my WhatsApp.
How kind of him. And to make sure that that is working, let's check the resistance between this and this. And it says about 0.4. Let's check to see what the schematic says it is. Yep, 0. So that's fine. So we repaired that. That basically is a fuse, and it did bust. Okay. Now, normally when we replace a backlight fuse, we also have to repair some further issues down the road. However, it looks like this backlight fuse blew because of the amount of liquid that was on the machine. So I don't think we're going to have a short further on down the road on this specific one. We just need to simply replace this fuse. And our solder here is a mixture of salt water and oxidation, so we need to add a little bit some solder to it in order for it to come off. Still not wanting to come off some, so let's add it with some heat. And just to make sure that there's not a short, we're going to test for any short to grounds. This side's good. This side's good, so there's no short, which means our fuse should be fine after this. And it doesn't really matter the orientation for a fuse, because a fuse is just a fancy wire that blows after it gets too much current going through it. There's not really an orientation on it. I know the P was going the other way. Okay. Now let's hook it up to our power supply and see if it blows. just to confirm we fixed our backlight issue. Okay, looks okay to me. Now we really won't know for sure if it's going to blow until we actually plug it back into our machine. Now another thing is that trace in the bottom left of that MOSFET looks really bad. And that looks like it's connected to a couple of different things. Now my question is, does that come from anywhere else on the board? Nope, it looks like it just comes from the MOSFET. So this is just a test point, thank goodness. So it's okay if that's gone. Alright, so now let's just kind of reassemble this back together into the computer it came from. And see if we get a backlight. And then if so, this one just needs to be cleaned. And then we can reassemble it. How long we've been going on the stream now? 1 hour and 55 minutes. All because of a fuse. Resistor. All because of a resistor. Jeez. Freudian slip. Oh, cool, you got the screen out. All right, once I test this out, we'll check out the inverter board over there. All right, so we can actually see there's a good deal of corrosion right here where the backlight circuit was. Oh. What did I just do? Okay, we're back. I promise I'm trying to get faster with these repairs. Hold up. Okay, I was just installing the wrong board. I was like, there's a lot more chocolate milk on this computer. Here we are. Alright, so we're going to connect everything because we're going to do a quality control test, and once everything boots up and is fine, we're then just going to give this an ultrasonic cleaning to get rid of the rest of the liquid damage. Now, actually, is this cable fine? It looks okay. Now, to make sure I don't troll myself, let's see, is there a short now on the screen? There's not, okay. Sometimes you can have a short in the screen itself, so you won't know that there's an issue until you put everything together, and then that backlight fuse will blow. But there was no short. And for the sake of not damaging their data for this stream, I'm going to not put the solid state drive in. We just want to see a question mark. I'll even leave the battery unplugged. Alright, moment of truth. Let's see if all this is working now. My fuse! Get out of here.
So do you want me to open up this XS Max? Or
Yes.
I tried to turn it on, but that didn't happen. So we basically just want to open it up and see if it exploded.
Mm-hmm. Or see if there's any signs of liquid damage. My fuse that I took off of the backlight area is stuck in the charge port.
How'd you manage that?
Oh, it's
Oh,
metal.
you did it.
Yeah. Come here. You can leave. This is not your home. Okay. Gone.
Did you get
Yeah.
Oh,
All right. Moment of truth. You gonna turn on? All right. We're pulling booting voltage or amperage, and this should spin. That was one time. Let's go. There's our second time. And then here's our third time. Okay, so that's a chime. And come on, question mark. Give me a question mark. It looks like the backlight's booting, but I'm waiting for a question mark. Come on. Nothing yet. Come on. Nope, backlight's still not working. I just put my flashlight underneath and I can see the question mark is flashing.
Okay, so you just need to do the backlight now?
So something is still wrong with the backlight, even after replacing the driver. So we're not done yet. Let's see, what did we miss? Is the backlight even getting power? This MOSFET here is probably bad. Oh, microscope camera's not working anymore. Okay, well, I'm probably going to end the video here anyways, just because we need to get back to work. What I'm going to do is just test and see if we are even getting a some voltage on the backlight. .5 on one side, 8.5 on the other. So we are getting some sort of power. So now the next thing I'm going to replace, in fact, I could probably do it real quick. Next thing I'm going to replace is going to be this really dirty MOSFET. But the microscope camera is not working anyways. But, okay, hold on. Let me check and see what I can see here. Okay, so our backlight fuse goes all the way up to, it can go all the way up to 32 volts. So what are we missing here? We're getting 8 volts. So we could either be missing a LCD backlight enable line, or this MOSFET is supposed to be 12 volts. I think 12 volts when it's on. Okay. EDP backlight enable, PB bus, LCD backlight. It's only we're only getting 8 when it should be about 12. We have a couple of resistors around it. All right. Well, I'm going to have to stop the stream for now, and I'll continue this in a part 2. It is lunchtime, so I hope this has been somewhat informative. We were able to figure out at least how to get PP bus working. Now we need to fix our backlight. So thanks so much for watching.